More than 1,000 feet above the Pacific, on the dry southern slope of a Hawaiian island almost no tourist visits, sits a bed of ocean coral. Not near the water, 1,000 feet above it. Broken shells, reef rubble, rounded beach stones, cemented into the hillside of Lanai at an elevation where nothing from the sea has any business being. Walk the slope, and you can pick the fragments out of the dirt by hand. The unmistakable architecture of a shallow reef, the kind of thing that grows only in warm water a few feet deep, now baking in the sun in a place where the nearest surf is 1,000 vertical feet below your boots. On the northern flank of the Big Island, on the slopes of Kohala, deposits like it climb higher still, nearly 1,300 feet. Something carried the ocean up the mountain and left it there. Whatever did it happened before any human being lived on these islands, and it will happen again. 1.5 million people live on this archipelago today. The volcano responsible has not stopped moving. It is moving right now, as you watch this, sliding toward the sea at 3 times the speed your fingernails grow. The Hawaiian Islands are the most beloved volcanoes on Earth. Kilauea draws crowds to watch rivers of orange lava crawl politely to the coast. The eruptions are photogenic. The lava is slow. Tourists stand 100 yards from it and take photographs, and the worst that happens to most of them is scorched shoe rubber and a memory card full of glowing orange. Hawaii is where people go to see a volcano and feel safe. And that reputation is the single most dangerous thing about the place. Because Hawaiian volcanoes do not kill with lava. They kill by falling apart. Every island in the chain is a mountain built too fast and too tall on a soft ocean floor, and every one of them, sooner or later, collapses into the water it stands in. When it goes, it does not erupt. It slides.
And the sea, shoved aside by a piece of mountain the size of a state, does not forgive. Other coastlines have learned this lesson, each in its own century, each at its own cost. Indonesia learned it most recently. On the 22nd of December, 2018, the flank of Anak Krakatau slid into the Sunda Strait in under 2 minutes, with no eruption large enough to warn anyone, and the wave it made killed more than 400 people in the dark. There had been no earthquake to trip the alarms, because the collapse itself made no earthquake worth the name. The first warning most people on those beaches received was the water. Papua New Guinea learned it in an earlier age. In March of 1888, the volcanic island of Ritter, a steep cone rising from the sea between New Britain and Mboy, collapsed almost entirely into the water in a single morning, and the waves it launched swept across the neighboring islands, drowning villages that had no idea the mountain across the strait had ceased to exist.
Japan learned it in 1792, when the flank of a volcano called Unzen gave way and slid into the Ariake Sea, and the tsunami that rebounded off the far shore killed roughly 15,000 people. Still the deadliest volcanic disaster in the recorded history of that country, and it was caused not by fire, but by a mountain falling into water. Norway learned it 8,000 years ago, when a slab of the seafloor the size of a small country broke loose off the coast and sent a wave across the North Sea that ran more than 20 meters up the cliffs of Shetland and helped drown the low land bridge that once connected Britain to Europe. That country of hunters and marshes, a whole landscape of people, simply ceased to exist. The Canary Islands have been watched for the same kind of failure, and Hawaii has already produced the largest ones the planet has on record. Same mechanism, same soft foundation, same arithmetic. The ocean floor does not care that we call the place paradise. For most of the 20th century, none of this was in the textbooks. The islands were volcanoes, and volcanoes erupted, and that was the story. The coral on the heights of Lanai was treated as a curiosity, a puzzle, a mistake in the rock. Perhaps the water had been higher once. Perhaps the land had risen. Perhaps some slow and forgettable process had lifted a reef and left it stranded. The idea that a wave could climb 1,000 feet up a mountainside was, to a serious geologist, absurd. Waves are a few feet tall. They break on the beach. The notion belonged to myth, to the old stories the islanders told, not to science. And so the evidence sat on the hillside in plain daylight for decades, and the question went unasked. The land was showing the answer the whole time. Nobody was willing to read it. So a few questions are worth putting on the table before we go further. Why do the gentlest volcanoes on Earth, the ones that never explode, produce the most violent waves on Earth? Who decided that the ocean stranded 1,000 feet up a mountain was an accident rather than a record? Why is the center that warns the entire Pacific about tsunamis based on low ground on Oahu, close to the very ocean it exists to monitor? And if the mountain is measured, the slide scars are mapped, the recurrence is known, what, exactly, are 1.5 million people waiting for? By the end of this video, 3 things will be clear. It will be clear why one geologist at the United States Geological Survey spent years mapping the pitch-black seafloor around Hawaii and found not one collapse but 68. It will be clear why the coral on the heights of Lanai should not exist, and what its existence proves. And it will be clear what the first 40 minutes look like across the entire Pacific Ocean after a Hawaiian flank finally lets go, minute by minute, in cities that have been told for 100 years that they are safe. The 29th of November, 1975, 4:48 in the morning. On the remote southern coast of the Big Island, at a place called Halape, 32 people are asleep on the beach. A Boy Scout troop, some park staff, a few hikers who walked in the day before across the lava fields, because Halape is one of the most beautiful campsites in the Hawaiian Islands. A curve of black sand under a grove of coconut palms, a warm lagoon behind the beach, low cliffs rising a few hundred yards inland, the ocean in front, and no road for miles in any direction. The nearest help is a full day's hike away across hardened lava. The night is warm and still. The tide is ordinary. The people on the sand have laid out their sleeping bags between the palms and the water, and they have no reason to be anywhere but exactly where they are. At 4:48, a moderate earthquake rolls through and wakes most of the camp. It is unsettling but not frightening. Hawaii shakes often, and the ground here is always muttering. Some people get up. Some check on the horses tethered in the grove. A party had ridden in with pack animals. A few decide to move their sleeping bags closer to the cliff, away from the water, on the instinct that solid rock is safer than open sand. A little over an hour later, at 3 minutes past 6, just as the sky begins to gray toward dawn, the ground does something none of them have ever felt. The entire south flank of Kilauea, a slab of mountain 40 miles wide, lurches toward the ocean all at once. The shock is a magnitude 7.2, the most violent earthquake in Hawaii in more than a century. The beach at Halape drops. Not shakes, drops. In seconds, the black sand sinks more than 10 feet, and the ocean floor beneath the campers falls with it. The palms lean. Boulders the size of cars break loose from the cliffs above. The very cliffs some of them had moved toward for safety, and come down through the trees in the dark. People are thrown flat and cannot stand. The horses scream and bolt. And then the sea, which had been lapping quietly at the sand a moment before, goes silent and pulls back from the shore, draining away into the dark as if something enormous had inhaled. Some of the campers, half awake and blind in the pre-dawn, run toward the cliffs, toward the rockfall, because falling rock is the danger they can hear. Others run along the beach. Not one of them understands, in that first minute, that the ground has just dropped them below sea level, and that the ocean is coming back to fill the space it was pushed out of. The first wave arrives within a minute or two of the shaking. It sweeps over the sunken beach, past the palms, and slams the survivors against the cliff face they had been trying to reach. It drags them out, then throws them back, then drags them out again. Witnesses later described being pulled underwater in total darkness, tumbled among snapped tree trunks and thrashing horses and their own gear, surfacing to grab at anything solid, going under again as the next surge came through. One man was carried out over the drop-off and swam for his life in the black water, watching the shore he had slept on vanish.
The largest wave that morning ran up to a height of nearly 50 feet. 2 people were killed, one a park employee, one a member of the scout party. 28 more were injured, some badly, all of them now stranded on a wrecked coast a day's hike from a road, in the dark, with the ground still shaking. A grove of coconut palms and a curve of black sand that had existed for generations were simply gone, dropped bodily beneath the Pacific, where the drowned lagoon and the sunken beach remain underwater to this day, visible to divers as a ghost shoreline a few feet below the surface. Rescue helicopters reached the survivors after sunrise. The dead were harder to recover. The people at Halape survived a small tremor of the thing this video is about.
A single earthquake nudged the flank of Kilauea a few feet seaward, a few feet out of the 40 miles of mountain that make up the block. And that few feet of motion was enough to shove a 50-foot wave onto one beach and kill 2 people on it. The magnitude 7.2 of 1975 was the flank clearing its throat. And it was not even the first time in the written record that these mountains had done it. Go back another century, to the 2nd of April, 1868. The southeast flank of Mauna Loa, the neighbor of the flank at Halape, and the largest active volcano on the planet, lets go in an earthquake larger than anything Hawaii has produced since. The shock is estimated near magnitude 7.9, and it does not merely shake the district of Kau, it rearranges it. Stone walls fall for miles. On the slopes above a place called Wood Valley, the violent ground motion turns a rain-soaked hillside to liquid, and a wall of mud, water, and shattered rock a mile wide slides down onto the settlement below, burying people, animals, and homes in seconds beneath a moving mass that no one on the ground could outrun. Along the Kau coast, the seafloor drops, and the ocean answers within minutes. A tsunami sweeps ashore over the low fishing villages, tearing houses off their foundations and dragging entire families out to sea before the shaking has fully stopped. Survivors describe clinging to canoes, to trees, to the roofs of floating houses. When the shaking and the water finally still, the death toll across the district runs to roughly 80 souls. The people who lived through it describe the same sequence the campers at Halape would describe 107 years later. The ground dropping away, the sea withdrawing, the wave returning faster than a person can run. 2 flanks. 2 spasms in the written memory of these islands, a century apart, each one deadly. And both of them, as violent as they were, are minor compared to what the same mountains have done when they failed completely. Because the record of the complete failures is not on the beach, and it is not in any diary or missionary's letter. It is under 2 miles of ocean, and for most of human history, no one had ever seen it. James Moore had spent his career listening to Hawaiian volcanoes, and by the 1980s, he had begun to suspect that the accepted story about them was missing something enormous. Moore was a geologist with the United States Geological Survey, careful, patient, the kind of scientist who trusted measurements over intuition and disliked being told something was impossible before it had been checked. The intuition of his entire field said the Hawaiian volcanoes grew steadily, layer on layer, and eroded slowly, grain by grain, like any other mountain worn down by rain and time. But the shape of the islands bothered him. The submarine slopes fell away too steeply in some places and far too gently in others. The coastlines had strange, curved gouges cut into them, as though something had bitten pieces out of the islands. It looked less like the slow work of erosion and more like something had been torn away all at once. To know for certain, he needed to see the seafloor, the vast, dark 2/3 of every Hawaiian volcano that lies below the waterline and had never been mapped. And in the 1980s, for the first time in history, the tools existed to do exactly that. The instrument was called Gloria, a torpedo-shaped sonar array longer than a car, towed on a cable behind a survey ship. It swept the ocean bottom with sound and listened for the echoes, and from those echoes it built an image of the terrain in water miles deep, in total darkness, where no eye and no light had ever reached. Across several years in the mid and late 1980s, survey ships dragged Gloria back and forth across the deep waters surrounding the Hawaiian chain, running long parallel tracks day and night, stitching together thousands of square miles of a seafloor that no human being had ever seen. And as the images came back to the ship and were assembled panel by panel, the comfortable old history of the islands quietly fell apart. The slopes below the waterline were not smooth. They were buried under debris, vast, chaotic fields of broken rock and tumbled blocks spilling out from every island, running for 100 miles and more across the ocean floor, fanning out into the abyssal plain like the frozen wreckage of avalanches caught in the act of moving. The islands had not grown quietly. They had been coming apart, again and again, throwing pieces of themselves across the deep ocean for as long as they had existed. When Moore and his colleagues finished counting, they had found 68 of them. 68 major landslides along the Hawaiian Ridge, laid down over the last 5 million years. Some of them among the largest landslides known anywhere on the surface of the planet, on land or underwater. The paper he published in 1989 gave them a plain and honest name: prodigious. The largest, off the north coast of Oahu, is called the Nuuanu Slide, and its dimensions refuse to fit inside ordinary description. It carried away a huge piece of the ancient Kilauea volcano, the mountain whose eroded remnant is now the sheer green wall of the Kilauea Range behind Honolulu, and flung the debris more than 130 miles out to sea. The volume of rock involved was on the order of several thousand cubic kilometers, enough to bury an entire American state hundreds of feet deep. And the debris did not simply spill to the bottom of the slope and stop. It had so much momentum that parts of it ran uphill on the far side of the deep ocean basin, climbing hundreds of meters up the flank of the rise beyond, the way water thrown into a bathtub sloshes up the far wall before it settles. To push that much rock that far and then force it uphill at the end of its run requires a velocity and a violence that the mind resists. The slide did not creep, it flew.
Inside that debris field sits the single detail that makes the scale impossible to argue away. A whole, intact block of the vanished mountain, torn loose and carried out with the slide, still stands on the sea floor 140 miles from Oahu. It is called the Tuscaloosa Seamount. It is larger than the island of Manhattan, and it rises nearly a mile from the ocean floor. A piece of a Hawaiian island the size of a city, an entire mountain in its own right, ripped off in one motion and dropped on the abyssal plain 140 miles from where it began. That is not erosion. No rainstorm, no river, no slow passage of time moves a block the size of a city 140 miles. That is a mountain coming apart, and the physics required to carry a fragment that large, that far, is the physics of catastrophe. The whole flank letting go at once, in minutes, and racing down the slope with enough energy to shove a city-sized boulder most of the way to the horizon.
Which brought Moore back to the coral on Lanai. Working with his brother George, another USGS geologist, he studied the strange marine deposits that climb the island's southern slope to more than 300 meters above the sea. The reef rubble, the beach cobbles, the fragments of shell, all cemented into the hillside far above any tide or storm surge that has ever existed. In 1984, the Moores published their conclusion, and it was the kind of conclusion that gets a scientist quietly mocked in the hallways at conferences. The deposit, they argued, was laid down by a single giant wave, a wall of water that had swept up and over the flank of the island roughly 100,000 years ago, and reached heights that no wave in recorded human history had ever approached. Later work by other geologists traced deposits like it even higher, onto the slopes of Kohala on the Big Island, and tied them to a specific submarine collapse off the Kona coast, the Alika Slide, roughly 120,000 years old. The wave that carried the ocean up those mountains, if the interpretation holds, reached a run-up height near the top of a 90-story building. A wave taller than any skyscraper in most cities on Earth, breaking over the shoulder of an island. The interpretation is not settled, and honesty requires saying so plainly. Some geologists argue the coral deposits were lifted gradually by the slow flexing and upward bowing of the crust under the weight of the islands, then reworked over long spans of time by ordinary storms and more modest tsunamis, and that the single giant wave picture pushes the evidence too hard. The debate is genuine, and it is ongoing, and a good documentary does not pretend a scientific argument is finished when it is not.
But here is the thing the debate cannot make disappear: the seafloor. The 68 landslides are not a hypothesis. The Tuscaloosa seamount is not a hypothesis. The debris fields the size of states are mapped, measured, sampled, and photographed. Whatever moved the coral up the slope of Lanai, the mountains around it demonstrably fell into the sea, repeatedly, catastrophically, throughout the entire life of the islands. The only question still open is how big the resulting waves were. And every time the geology is pressed on that question, it answers the same way: bigger than anything a human being has lived to describe. The mechanism behind it is not mysterious. It is, if anything, obvious once you understand what a Hawaiian volcano actually is. Picture a child building a sandcastle by dribbling wet sand into a cone.
The cone rises fine, higher and higher, until it passes a certain steepness, the angle the wet sand can hold. And then one whole side of it slumps away at once, without warning, in a single collapse. A Hawaiian volcano is that cone, only it is 5 miles tall from its base on the deep ocean floor to its summit in the air. And it is built by lava piling onto lava, eruption after eruption, faster than the soft seafloor beneath it can bear the growing weight. The mountain is loading itself, higher and heavier every century. And inside the pile, the problem is worse than simple weight. Deep in the structure lie old layers of ocean sediment and weak, chemically altered rock. Slick, clay-rich zones that behave like grease smeared between the heavier layers stacked above them. Magma rising through the cone pushes the whole flank outward along those greased surfaces, a fraction of an inch at a time. So the volcano is not merely too tall and too heavy and too steep. It is being actively shoved toward the edge from the inside, by the same rising magma that builds it. Every eruption that makes it taller also nudges it closer to the day it fails. The eruption is not the disaster. The eruption is the thing that loads the gun. Consider how strange that makes these mountains as a hazard, and how it inverts everything the tourist brochures imply. Every other volcano on the danger list announces itself before it kills. A stratovolcano, the classic steep, explosive cone, swells and steams and swarms its seismographs for days or weeks before it blows. And the warning comes first, and the eruption second. A Hawaiian flank offers no such courtesy. It can slide on a day when the volcano is entirely quiet, when nothing is erupting, when the summit is calm and the visitors are photographing the lava at a comfortable distance somewhere else on the island. The trigger might be an eruption pushing magma into the flank. It might be a large earthquake far below. It might be nothing more dramatic than the slow arithmetic of gravity finally winning against friction on a clay layer that has held the flank in place for 10,000 years, and simply, on one ordinary afternoon, stops holding. The disaster does not need permission. It does not need a plume of ash or a river of fire to announce itself. It needs only for the flank to reach the angle it cannot hold, and no one standing on the surface will know that angle has been reached until the mountain is already in the water and the sea is already climbing. If the story of the planet's hidden catastrophes, the ones that never made it into the textbooks, is the kind of thing that pulls you in, subscribe to the channel and turn on notifications. There are more of these ahead, and every one of them is real. And now, back to the mountain that is still moving. The south flank of Kilauea has a name among the scientists who watch it. They call it the Hilina Slump, and it is the most closely monitored, unstable slope in the United States. It is the same 40-mile block that lurched at Halape in 1975. It has not stopped. GPS instruments bolted to bedrock across the flank show it creeping steadily seaward, on the order of 3 inches every year, 2 to 3 times faster than a fingernail grows, a whole block of mountain 30 miles across, sliding toward the open ocean in slow, silent, continuous motion that never rests and never reverses. Most years the creep is smooth and gradual, too slow to feel. Then the flank catches on a sticking point deep below, strain builds behind it like a drawn bow, and the stored energy releases all at once in a jolt, the way it did in 1868, the way it did in 1975. In the spring of 2018, when Kilauea's summit floor collapsed and lava tore open the ground in a lower neighborhood called Lanai Estates, the flank produced its largest earthquake since Halape, a magnitude 6.9 that shifted the whole block seaward again in a single day. For a moment, the mountain reminded everyone what it actually is. Not a fixed and permanent thing, a landslide in progress, occasionally pausing to catch its breath. How the flank finally fails, whether it goes as one catastrophic slab or in a slower, staged collapse spread across hours or days, is the single largest question hanging over the science, and it is the entire difference between a regional emergency and an ocean-wide one. A slump that creeps and jolts and creeps again may never produce the mountain-climbing wave of the deep past. It may simply keep grinding seaward for another 10,000 years, shedding its stress in survivable increments. But a coherent flank that detaches all at once, tens or hundreds of cubic kilometers of rock breaking free in a matter of minutes, is precisely the machine that stranded coral on the heights of Lanai. The seafloor records both kinds of failure. The 68 slides in Moore's catalog are not all giants. Many of them were smaller, slower, staged events that a coastal community could survive. But the giants are in there too, unmistakable in the debris, and nothing in the geology promises that the next one must be small. Nobody can tell you the year the Hilina slump will fail completely, or whether the next great Hawaiian collapse will come from Kilauea's flank at all, rather than from one of its neighbors, the western flank of Mauna Loa, or the submarine giant of Kameahuakanaloa, formerly known as Loihi, the youngest volcano in the chain, already building itself toward the surface off the southern coast of the Big Island. What the geology allows us to describe is not the when.
It is the what. So consider the what, the way the scientists model it, the worst plausible case, played forward from the moment a major flank finally detaches. The failure begins underwater, along the greased clay layers deep in the pile, and it moves fast. A slab of mountain, tens, perhaps hundreds, of cubic kilometers of rock, breaks free of the island and begins to slide down the submarine slope, accelerating as it goes, tearing loose more of the flank as it moves. On the surface directly above the slide, the sea is yanked downward and outward as the seafloor drops away beneath it, and the surrounding ocean rushes in to fill the collapsing space, piling into itself and rebounding upward into a dome of water miles across. That dome is the wave. And from the instant it forms, 3 things begin to fail in sequence, each one on its own clock, each one measured against how far it sits from the mountain that just came apart. The first thing to fail is the nearest coast.
On the Big Island itself, the shoreline closest to the collapse has no warning and no time whatsoever. The run-up here is measured not in feet but in hundreds of feet, a wall of water that overtops the coastal cliffs and drives inland across the lava fields and the coastal roads before most people have finished registering that the ground shook at all. The communities along that coast, the small towns and harbors of the Kau and Puna districts, the scattered homes, the single coastal highway that is the only way in or out, sit directly at the foot of the very flank that is failing. For them there is no evacuation, because a wave born from your own island arrives in the time it takes to stand up from a chair. Boats in the harbors are lifted and thrown inland.
The highway that would carry people to safety is itself underwater in the first minute, its bridges gone, its lava rock roadbeds scoured away. Survival on the nearest coast is not a question of warning systems or of running. It is decided entirely, and in advance, by whether a given person happens already to be on high ground when the mountain enters the sea.
The second thing to fail is the rest of the chain. The wave crosses the open channels toward the other islands, and the clock it runs on is measured in minutes, not the comfortable hours that a distant earthquake gives. Maui, Molokai, and Lanai lie closest, some of them directly across the channel from the failing flank, close enough that the water reaches them almost before the shaking on the Big Island has stopped, with almost nothing on the clock. And then Oahu. Nearly 1 million people live on Oahu. The hotels of Waikiki stand a few feet above the tide line, packed with tens of thousands of visitors who came for exactly that view. Downtown Honolulu sits on low, reclaimed coastal ground, much of it built out over Old Harbor and Reef. The runways of the international airport are laid out on fill and reef flat at the water's edge, a few feet above sea level. And the single, deep-draft commercial harbor that feeds the island, the harbor through which nearly everything the island eats, burns, and builds with, arrives by ship, sits at the same low elevation. A wave born from a major flank collapse could reach that coast in roughly half an hour to 40 minutes. On a shoreline that low, that dense, and that crowded, half an hour is barely time enough to sound the sirens, let alone move a city off the coast and up the hills behind it. The tsunami that killed people in Japan in 2011 gave those coastlines minutes. The distant tsunamis Hawaii is built to expect, the ones born from earthquakes in Alaska or Chile, give the islands hours and a fighting chance. A wave from Hawaii's own mountains gives Hawaii almost nothing. The third thing to fail is the ocean itself. A wave large enough to strand coral 1,000 feet up the slope of Lanai does not stop at the edge of the archipelago. It radiates outward across the entire Pacific basin, carrying its energy toward every shore that faces the same water. Hours after the Big Island coast is overrun, the leading edge reaches the shores of California and the Pacific Northwest. The low coastal cities of Los Angeles, San Diego, the port districts, the beach towns. Hours more, and it arrives on the coasts of Japan, the Philippines, Chile, the whole ring of nations that face the Pacific, and the hundreds of millions of people who live along their shorelines. The energy that a distant earthquake spreads gently and thinly across the sea, a flank collapse concentrates and hurls in a coherent pulse.
Every serious model of these events carries the same honest caveat, and it deserves to be stated. Most simulations produce waves at the far shores that are large but survivable, not the mountain-climbing monsters of the deep geologic past, and the true size depends entirely on how fast and how coherently the flank fails. A staged collapse makes a smaller, more merciful wave. But every model, cautious or not, agrees on the shape of the thing, a local annihilation beyond any possible warning, radiating outward into an ocean-wide event, from a source that 100 million people around the Pacific have been taught their whole lives to think of as a vacation. And then comes the part that does not end when the water goes back. The aftermath, which for a place as isolated as Hawaii is its own slow disaster. These are the most remote populated islands on Earth. Nearly everything arrives by sea.
Roughly 4/5 of what the islands consume, food, fuel, construction material, medicine, comes in through a small number of low-lying harbors, and the largest of them sits on exactly the coast the wave would strike. Break the harbors and the runways in a single morning, and the resupply line to 1.5 million people is severed at both ends at once. The fuel that runs the power plants and the vehicles moves through coastal terminals built at the water's edge. The power plants themselves, the desalination and water treatment infrastructure, the sewage systems, the communication cables that come ashore on the beaches. All of it clusters on the low ground near the sea, because that is where the harbors and the cities are, and all of it lies inside the reach of the wave.
In the weeks after, the survivors on high ground would face an island with its port gone, its airport flooded, its fuel terminals wrecked, its grid down, and no road that leads anywhere off the island, waiting on relief that must itself come across the same ocean and land somewhere that no longer has a working place to land. The wave is over in an afternoon. The isolation it leaves behind is measured in months.
The preparedness gap is where the story turns from geology into something harder to look at. The science has done its work, and done it well. The 68 slides are mapped. The Hilina slump is wired with GPS and watched around the clock by the Hawaiian Volcano Observatory. The inundation zones are drawn on the maps. The sirens are mounted on poles along the beaches. The evacuation routes are painted on the roads and printed in the front of the phone book. And yet the Pacific Tsunami Warning Center, the facility responsible for alerting the entire ocean, the nerve center that warns coastlines from Alaska to New Zealand, sits on low ground in Honolulu, surrounded by the same ocean it exists to monitor. The whole system is built, sensibly and correctly, for the tsunamis it was designed to catch, the ones that come from far away, that a seismograph detects the instant the distant earthquake strikes, and a computer tracks patiently across hours of open water while sirens sound and highways fill. It is not built, and perhaps cannot be built, for a wall of water that leaves a neighboring island and arrives before the alert can even be written. The warning network watches the far horizon with great care. The nearest and largest threat is under the mountain in its own backyard. The flank is moving as you read this sentence. Not as a figure of speech. The GPS receivers bolted to the south side of Kilauea are recording the displacement right now, in real numbers, a few inches a year, the block sliding seaward while the island sleeps and the visitors photograph the lava. The mountains of Hawaii are still being built, lava on lava, taller and heavier and steeper with every eruption, which means they are also, with every eruption, a little closer to the angle they cannot hold. The same process that made the islands is the process that periodically destroys them, and in 5 million years, it has never once stopped. The 68 collapses in the record are not the end of a list. They are the entries written so far. There is a kind of humility built into these islands that almost none of the people standing on them ever feel. Every Hawaiian island is a mountain in the slow act of falling into the sea. The sheer green wall behind Honolulu is the scar left where half of an older mountain already went, 100 miles of its bulk now scattered across the ocean floor to the north. The beaches, the resorts, the runways, the harbors, the neighborhoods where people are raising children, all of it rests on the shoulders of volcanoes that are, on a timescale longer than any human memory, avalanches paused between one collapse and the next. We build on the top of the slide and call it solid ground, because in a single human lifetime it does not move enough to notice, and a lifetime is the only ruler most people ever use. The calibration is the error. The land is older than the calibration. It was falling long before anyone arrived to name it, and it will be falling long after the last name is forgotten. The coral on the heights of Lanai is the only witness that was actually there. It cannot tell us the year the wave came, or the day, or the hour. Wood keeps time in rings, and mud keeps time in layers, but a bed of shattered reef 1,000 feet up a dry mountainside keeps only a single fact, and it keeps that one fact perfectly, forever. The ocean was here, at this height, once, and something the size of a mountain put it here. The deposit does not argue, it does not predict, it does not exaggerate or soften. It simply sits on the slope in the sun, 1,000 feet above where it belongs, in plain daylight, waiting for anyone to walk up and read what it says. If the deep memory of the planet, the catastrophes it has already survived, and the ones it is quietly preparing, is the kind of thing you want more of, subscribe and turn on notifications so the next episode finds its way to you. There are more mountains carrying this story, and more coastlines worth listening to. Somewhere off the Kona coast, and somewhere under the south flank of Kilauea, and beneath every island in the chain, slabs of rock that have failed before are being pushed, inch by inch, year by year, toward the moment they fail again. The slides are mapped, the block is measured, The wave has already climbed the mountain once, and the coral on the heights is still there to prove it did. The question is not whether a Hawaiian mountain will fall into the sea.
The record makes that certain. The question is which flank goes first, how much of it moves at once, and how many of the 1.5 million people who live in its shadow are on high ground when the ocean comes back for what it left on the hillside. The ledger of the Hawaiian Ridge holds 68 entries. The 69th has not been written yet.